Welcome to another deep dive.
We can see how that led to our current picture of the universe and all the amazing stuff in between.
I'm in. Let's do it.
I hope we will have very successful and happy. Good morning, everybody. Today we will okay. Good morning, everybody. Today we will continue with Newton's laws of motion. So again, we will deal with motion, but we will take the forces into the account. So force, and then they will in physics. And then why forces are vectors. We will use forces as vectors, and then they will have vector components. And we will also talk about the significance of the net force on an object. Net force, you can say, a vector sum of all forces act on an object. We will deal with this one. Force object is in it and that's three mathematics. This movie net principles of this. So this is the main difference between kinematics and dynamics. Within the dynamics, we have forces. Within the kinematics, we don't deal with the forces, we just describe the motion. So the principles of dynamics stated for the first time by Sir Isaac Newton, and today we call them Newton's laws of motion. So as I told you at the beginning, we have three laws. And within this chapter, we will learn them step by step. So now let's discuss the properties of a force, first of all. A force is a push or a pull. For example, here there's a mass, and this is hand of somebody, and then he or she pushes this mass. So then we have a force acting on this object. Or there is a rope here, and then you are pulling this object with some certain force. This is push, this is pull, okay? And another property of a force is an interaction between two objects, or between an object and its environment. We will discuss this one. A force is a vector quantity, as we have shown here with an arrow on top of it, this magnitude and direction. So you know already each vector has certain magnitude and direction. So if we are dealing with the forces, you have to use this information. And we have four common types of forces. So don't forget this one, four common types of forces. Normal force, friction force, tension force, and weight due to the gravity, okay? Four forces, weight, tension force, friction force, and normal force. Now let's describe them step by step. So what is normal force? Here we have an object, and this is the ground, let's say, and this object has certain mass, okay? Due to the gravity, this object applies a force on this surface, and then this surface applies a back force to this object. So this is called as normal force. Definition is here: when an object rests or pushes on a surface, the surface exerts a push on it that is directed perpendicular to the surface. So here we have an horizontal surface. If you have such surface, then the direction of the normal force perpendicular to the surface, okay? Don't forget this one. The normal force is always perpendicular to the surface. Normal force is a contact force. What is the meaning of the contact force? So there is a contact between this object and this surface. Let me show you here with a pen. We have a surface here, and then we have object. Let's say it is hanged. So there is no normal force here. There is another force. I will describe this in the forthcoming transparencies. So in order to have normal force, we need a contact, okay? We have a contact here, and here we have a contact. For this reason, normal force is a contact force. Now let's continue with the friction force. Friction force is also a contact force. Leg of her father or leg of her mother, I don't know. So what are the forces? So you need a contact between the object and the surface of the material or surface of the ground. So in addition to the normal force, a surface may exert a friction force on an object directed parallel to the surface. So normal force perpendicular to the surface, but the friction force is parallel to the surface. The direction of the friction force can be either in this direction or in this direction, depending on its movement, depending on the conditions in the problems, okay? But it must be parallel to the surface. Normal force is perpendicular to the surface. And sometimes we consider that this surface is frictionless, okay? In such cases, the friction force will be zero, okay? But sometimes the friction force for this force is required. To pull objects over a distance, so what you have here, same condition. So this is moving the friction object, the reaction. Okay, now let me give you some examples of common forces. Maybe first of all, I should mention the unit of the force. The SI unit of the magnitude of force is Newton, okay? And shortly we show it as N, capital N. So here we have some typical force magnitudes. Weight of a large blue whale, for example, 1.9 times 10 to 6 Newton. Maximum pulling force of a locomotive, for example, 8.9 Newton. And to the gravity in the hydrogen atom at the beginning of vector. I have to continue with the force is a vector, okay, and I can represent here, okay, as the in terms of two, which second force acting or force one must use or here the force acting on all forces. So this is another here, and it's an important term which is C one velocity. When a body acting on air have very then let me continue with the Newton's first law. Here I have very important term which is called as equilibrium, denge. Okay, you will see this term in every forthcoming chapter, if the system is in equilibrium, then it means that the net force acting on the system is zero. Okay? Within the Newton's first law, we will discuss this one. When a body is either at rest or moving with constant velocity, we say that the body is in equilibrium. Now let me draw these two conditions. So first condition, let's consider this is a box and this is a surface. There is a weight due to the mass and gravity, okay? And there is a normal force. Due to the weight, this box, this object applies a force on this surface, and then this surface applies a back force, which is called this normal force. Then what is net force here? If you choose this one is positive y direction, then the net force is n minus weight. Since they are equal to each other, the net force is zero. Then the system is in equilibrium. What is the meaning of equilibrium? It was at rest here, and it will stay at rest. If the system is in equilibrium, it will keep its initial condition. Okay, don't forget. This is the first condition here, when a body is at rest. Now the second condition, or moving with constant velocity. So let's consider that this body here, the same box, moving with constant velocity, okay? And let's consider that the friction is zero here. There is no friction. And there is a weight force. And there is another force, normal force. So the total force acting on this object along the y-axis is zero. Okay? But what about the force acting on along the x-axis? It is also zero, because the object is moving with constant velocity. If the velocity is constant, then acceleration is zero. If the acceleration is zero, there is no force. Okay? So this is equilibrium. Both conditions are equilibrium. Here, at the beginning, it was at rest. And since the net force acting on the system is zero, it is at rest. Okay? Then it is in equilibrium. Here, the object is moving in this direction, let's say, with some certain constant velocity. Acceleration is zero since the velocity is constant, and the net force acting on the system is zero. Then the body will continue to move in this direction with this constant velocity, because the net force acting on the system is zero. The system is in equilibrium. Okay, for a body to be in equilibrium, it must must be acted on by no forces or by several forces such that their vector sum, that is, the net force, is zero. Here, as we have discussed. So this is the Newton's first law. If the system is in equilibrium, if there is no net force acting on the system, or if there are several forces act on the system, but if their vector sum is zero, then the system is in equilibrium. This is the Newton's first law. Okay, now let's discuss this Newton's first law in this example. Here we have a hockey puck, and then we have here frictionless surface. And there is a force acting on this hockey puck. This is a contact force. You apply F1 on this hockey puck. And due to this force, this puck is accelerated. It has certain acceleration, okay? It is not in equilibrium. But if you apply same force in terms of magnitude, but in opposite direction, then here you have F1, here you have F2, and in magnitude they are same, but they have opposite directions. Then the net force acting on this hockey puck is zero, then acceleration is zero, and the puck is in equilibrium. This is the result of Newton's first law. And let's discuss again the Newton's first law in this example. Here there's a sled, in Turkish kızak, and here there is a child, and here you see a leg, okay, leg of her father or leg of her mother, I don't know. So what are the forces acting on this sled here? Let me show the forces. So let's consider that there is a friction element in this surface, and then here we have a friction force, okay? And this leg applies a force here. And due to the weight of this child and weight of the sled, there is weight, and we have normal force with equal amount of the weight, okay? So along the y-axis, let's say, let's choose that this is y, and let's choose that this is x. Along the y-axis, what is the net force? Net force is zero. Maybe I can also show this force along the x direction in order to simplify the question or situation. So let's consider that this leg applies force this direction. Okay, then what about the net force along the x? Net force along the x. Let's consider the force applied by the leg and the friction force are equal to each other. Then you can say that the net force acting along the x is also zero. So then this system is in equilibrium. If the sled at the beginning is at rest, it will stay at rest. But if this sled has certain velocity and movement at the beginning, then after this condition, it will continue to its moment, okay? Since the net force acting on the system is zero, okay? System is in equilibrium. You don't change the something within the system. Do you have any question here? Then let me show you two examples. This is the conceptual example 4.2 from the book. In the classic 1950 science fiction film Rocket Ship XM, a spaceship is moving in the vacuum of outer space, far from any star or planet. When its engine dies, as a result, the spaceship slows down and stops. What does Newton's first law say about this sentence? spaceship is moving in the vacuum of outer space, far from any star or planet, okay, then the net force acting on the spaceship is zero. So when its engine dies, it should continue to its movement since the net force acting on the spaceship is zero, right? But in the science fiction film, the spaceship slows down and stops. This is wrong, okay? Okay, another conceptual example. You are driving a Maserati Gran Turismo S on a straight testing track at a constant speed of 250 km per hour. You pass a 1971 Volkswagen Beetle doing a constant 75 km per hour. On which car is the net force greater? On which car is the net force greater? So Maserati has constant speed. Beetle has also a constant speed, okay? So speed is constant, acceleration is zero. If the acceleration is zero, then the force is zero. So both cars are in equilibrium because their velocities are constant. Newton's first law, therefore, says that the net force on each car is zero. Okay, so don't forget this. And let me continue with the inertial frames of reference. So suppose you are in a bus that is traveling on a straight road and speeding up. Okay, so it is speeding up. What is the meaning of speeding up? There is an acceleration, okay? Let's say it is speeding up in this direction. If you could stand in the aisle on roller skates, you would start moving backward relative to the bus as the bus gains speed. So let's consider that you are standing in the aisle. If you could stand in the aisle on roller skates, you would start moving backward. And so is that suppose you are in a bus that is traveling on a straight road and speeding up, okay? So it is speeding up. What is the meaning of speeding up? There is an acceleration, okay? Let's say it is speeding up in this direction. If you could stand in, okay? So it is speeding up. What is the meaning of speeding up? There is an acceleration, okay? So it is speeding up.